Hello, good morning. Hope I am audible.
Yes, madam, you are audible.
Yes, sir. Good morning, Dr. Mrityunjay Dodamani, sir, professor from NITK. This is an FDP program on 3D printing technology in engineering, education and research. Today is 6th day, a technical session on 3D printing of foam. I welcome all the participants for this technical session. Shall we start the session?
Yeah, shall I share my screen, madam?
I'll just read out your biodata. And
Okay.
Good morning, everyone. Welcome to the technical session on 3D printing of foam by Dr. Mrityunjay Dodamani, professor from NITK Surathkal. I'll read out a brief resume. Dr. Mrityunjay Dodamani is an assistant professor of mechanical engineering at NITK Surathkal. His research is focused on lightweight composites synthesized by industrial scale manufacturing routes and 3D printing. Dr. Mrityunjay's research has been supported by various funding agencies in India and abroad. He is a recipient of Visiting Scientist Fellowship by Office of Naval Research, USA. He has published over 70 journal publications and serving as an editorial board member on Materials Circular Economy journal by Springer Nature. He is inventor of 2 Indian patents and co-founded a startup in the area of 3D printing. Once again, welcome Dr. Mrityunjay Dodamani, professor from NITK Surathkal, for the technical session.
Thank you, madam. And I thank all the sponsoring agencies who is sponsoring this FDP and AMC Engineering College for giving me an opportunity to share my experiences. So, ma'am, shall I share my screen?
Yes, sir. Yes, sir. Yes, sir.
Okay, thank you. Just, ma'am, is the screen is visible in the presentation mode?
Not yet, sir. I think
it is getting loaded.
Yes, sir. Yes, sir.
Is it visible now?
Yes, sir. It is visible.
Okay, thank you. So I'll start now.
Yes, sir.
Just a minute. Yeah, thank you. So, good morning, ladies and gentlemen. Namaste to all of you. So, I am Mrityunjay from National Institute of Technology, Karnataka, Surathkal, and I'll be talking on 3D printing of foams. So, I'm affiliated to mechanical engineering. Before starting the talk, let me thank all my funding agencies, starting from Department of Science and Technology, SIRB, SPARC, ISHRI, Office of Naval Research Global, Singapore, USA, National Science Foundation, USA, and then VGST. Completed 3 projects and 7 DST projects are presently ongoing. All are in the theme of 3D printing. So I thank all these funding agencies for supporting my research group through various funding opportunities. So we are down south and we have a beach on campus, all of us know, and we are presently at NERF ranking 10. We are in top 10 band this year. Last year we were at 13, and we jumped to 10 this year. So let me talk about the foam. So there are two types of foams. One is a closed cell foam, another is open cell foam. So now I'm going to focus on closed cell foam. And these closed cell foams are also known as syntactic foams, which are realized by having hollow glass microballoons in the matrix. And you can just see this reconstructed three-dimensional image wherein we have these hollow microballoons in the matrix. It might be any matrix, polymer, in polymer, thermoplastic, thermosetting, metal, ceramic. We can infuse these hollow balloons in the matrix and we can synthesize foams. And this is how a typical microstructure looks like. Here in syntactic foams, we get one more additional dimension as far as the composites property is concerned. What I mean by this is, generally in composites, we talk about the volume fraction or weight fraction as against the property. It might be strength, density, moduli, and so on and so forth. For an example, let us take a moduli. So in general, in composites, we plot a two-dimensional graph wherein we say x-axis is the volume fraction of the filler or a reinforcement, and the y-axis is that property which in a present case, for an example, is a moduli. And then we plot a curve or we plot a response or a behavior wherein as the number of volume fraction of filler increases, what happens to modulus. In the syntactic foams, closed cell foams, we have one more axis at z-axis, wherein for a same volume fraction, we can have different wall thickness. You can see in this image, this is one wall thickness. I can vary this wall thickness. So for the same volume fraction, the wall thickness might be 1 micron, 5 micron, or 10 micron. So likewise, the wall thickness will increase here. So with increase in wall thickness, for a given volume fraction, what is that moduli property? So this is the z-axis, which gives an additional flexibility to tailoring these properties of syntactic foams for any given application. And thereby these syntactic foams are being widely used in aerospace, automobile, marine, biomedical applications, wherein you have to tune the moduli of an implant to the bone and so on and so forth. So here typically these microballoons are in the particle shape. Those are spherical in nature. Many particles are available. Glass are engineered ones, and those are commercially available. Fly ash cyanospheres are naturally burnt one, which are the environmental pollutants. So from the fly ash, you can extract the hollow particles known as cyanospheres and utilize them. So these are naturally abundantly available, which are environmental pollutant ones. So you can find and utilize it in components, products out of them. Engineered ones are available by many companies. In addition to the spherical one, we have cuboid ones, silicon carbide, Al2O3. But as these have corners, these induce stress concentrations within the system once you disperse in the matrix. And thereby, generally, we don't prefer these. We prefer the spherical. No stress concentration, and there will be uniform spread of a resin around this, because that is a crucial parameter in composites, wherein we talk about the wetting of matrix onto the reinforcement or a filler. There are many applications for composite systems: aviation, thermoforming plugs, wherein you bend the sheet in a specific form. So these are the plugs which are used to bend them. Now here we need minimum coefficient of thermal expansion, because during a mechanical process, heat gets generated. And if you can keep that minimum, then these plugs can easily release the sheet without any additional mechanism. And that's how many types of this foams plugs are available. Then widely used in seashore applications, wherein we're extracting oil somewhere at deep down the sea and transporting it to the shore. When we need to do that, we need to send this crude oil through a pipe, or oil through pipe, whatever fluid we extract there. If we don't rope it with this in the yellow colored modules, these are known as syntactic foam modules, the pipe sinks and there is every chance of rupture of a pipe and spillage of the fluid which the pipe is carrying. And that's how we rope them in these syntactic foam modules, which keeps them floating on the water, avoiding any damage to the pipe. There are many applications, as mentioned by Professor Nikhil Gupta in one of his paper in application of syntactic foams, wherein we have a human-operated vehicle Alvin, which is used to find the wreckage of a Titanic in 1960s, which carries 3 people on board, and we need the foam to be part of this module to go deep down the sea at a specific depth. And we have remote operated vehicle JSON, which is a maintenance module for underwater pipelines. At many areas of warship, it has been used as well. James Cameron used a completely made up of syntactic foam module known as Deep Sea Challenger. So in the present talk, I'm going to focus on what my research group was doing in the area of syntactic foams. We are exploiting high density polyethylene with cyanospheres, fly ash cyanospheres, which I mentioned, which is naturally pollutant one, and engineered glass microballoons as well. We kept the filler percent same so that we can compare apple to apple. Below 20%, when you infuse these reinforcement, which is in the spherical form, which is hollow in nature, we'll end up with higher density material, which is not suitable for buoyancy applications or lightweight structural, weight sensitive structures. Above 60, lot of particles or fillers starts interacting with each other in the matrix system. And there's every chance that particle to particle interact, they fail and they break. And then the density shoots up suddenly. And that's how we kept it same based on our pilot experimentations. We exploited many industrial scale manufacturing systems to produce these foams, starting with injection molding, compression molding, and recently 3D printing. And that's how my role in 3D printing of foams comes in picture as part of this talk. So I'll let you know why we jumped to 3D printing. Where was that gap we found out in 2016 to switch over to 3D printing, and therein where we explored the additive manufacturing route for manufacturing foams. And this work was collaboratively done with Professor Nikhil Gupta of New York University. So what we did as an outcome of the first PhD student from my group in 2016 is this. This is the image that is the thesis outcome of his PhD in 2016, wherein we manufactured syntactic foams components. All these are different components. You can see, we can read the names as well here. Through industrial scale manufacturing methodology known as injection molding. Konkan Specialty Polymers Limited from Mangalore supported us in this task, Conspec, wherein we used their injection molding machine in the shop floor. So this was completely an industrial scale development and not the laboratory scale development, wherein the laboratory scale development happens in very closed and controlled environment. So this was in the industry on the shop floor. What we could able to produce is, instead of having the high density polyethylene, which is the most commonly used polymer, thermoplastic polymer in the industry, instead of using the virgin plastic, we mixed hollow microballoons, which are known as fly ash, and thereby the color is changed to gray here, and shown the feasibility of producing fly ash reinforced, cyanosphere reinforced, which is treated as an environmental pollutant, to be used in the commercial components. And these components are very well known to us. If you look at this part, number 4, this is the electrical junction box, wherein 4 pipe comes through all these 4 channels, and then the wiring is done at the center. So here, now by having the fly ash cyanosphere it is an eco-friendly product. Pollutant is being used. Fire retardancy is more. And most importantly, this is the component which is having 60% of cyanospheres. That means 60% by volume or weight of the high density polyethylene version 1 is being saved. So by that sense, the carbon footprints are too low for this component. Everything went well except this component number 3, which I'll again show it to you here. So if you see this component number 3, which is a polymer gear, you can see the multiple patches, white patches here. And these multiple white patches signifies that the fly ash cyanospheres, which is gray in color, didn't reach to these locations. And the obvious reason is complex geometry, thin to thick section continuous change. And this made this component to fail. Fail in the sense it worked well, but appearance wise, but by dispersion of cyanospheres wise, this component did not show that prominence in injection molding. So as part of this problem which came up, the PhD thesis of my first student, Bharat, we proposed this problem to Department of Science and Technology System Development Program under Additive Manufacturing Technologies scheme way back in 2015. That this is the problem in injection molding, and then if we need to resolve this, 3D printing would be a viable option. So give us a funding, and that's what the first funding I got in 2016 to additive manufacture the syntactic foam, thermoplastic based. And as part of this 3D printing, as all of us know already, this is the 6th day you are going through. It's the CAD file, which we send it to a device known as a printer. And this CAD file converts it to a layered deposition at the printer level. So that means we have very high flexibility of design change without any additional penny for a tooling as against any other conventional manufacturing methodologies. So if I want to change the shape, I can just change the CAD drawing, the printer immediately starts printing and realizing that particular component in the next batch. So it's a highly flexible system. Tooling cost is 0, minimum lead time. So what I'm going to talk about is fused filament fabrication system, which is also known as FDM. FDM word is copyrighted, so thereby I'll use fused filament fabrication, wherein the wire or a filament, which is made up of polymer, is being fed to extrusion head. Extrusion head melts it and deposits based on whatever CAD file you have sent, which is getting converted to a machine language known as a G code. So it traces that path, and on a platform, you build a particular component. This is what setup we have at NITK Surathkal from 2016. All the machines are still running and are being exploited to the maximum potential. So here we have a 3D printer having volume of 500 cubic millimeters. So 500 millimeters by 500 millimeters by 500 millimeters, having temperature range of 450 degrees C. And we can utilize any filament we want. So this system costed me 20 lakhs, procured from AHA 3D in Jaipur, Rajasthan. Now, we manufacture our own filament as part of this DST project, which got completed in 2020. So for that, we have a single screw extruder, which is non-vented type. So here we feed the pallets, composite pallets, into the hopper, draw the wire, which is required for a 3D printer. Generally, two diameters are preferred. One is 1.75 plus minus 50 micron. Second is 2.85 plus minus 50 micron. So that we can manufacture here. So the composite blend is prepared in a polymer blender, wherein we mix the polymer and whatever filler you want, melt it, blend it. The blend comes out, we shred it, we chop it, load it into the hopper of an extruder. So this is the first heating cycle. Second heating cycle, and the third heating cycle. The third heating cycle is in this heated extrusion head. So likewise, there are 3 heating cycles the polymer comes across. So we need to really look around all the basic characteristics and characterizations of the polymer pertaining to TG, pertaining to melting point, pertaining to degradation temperature. And those parameters will set the limitations for blending, extrusion, and printing. And all these systems are available. These 2 we procured as part of DST grant. So whenever we talk about in-house filament manufacturing, and whenever the developmental efforts are for material innovation, then we need to devise, define, and develop our own material system. And that's how these 3 systems are being used for that. And when we do that, we need to find out a suitable parameters for blending, for filament extrusion, as well as for printing. So in this filament extrusion, we have barrel temperature, wherein we have a barrel here. There are 4 heating zones. This is procured from Asabi, Thane, Maharashtra. Then we have a die temperature, screw speed, and takeoff speed. These define the filament diameter, whichever way you want, whichever diameter you want. So barrel temperature and die temperature decides from the feed section to the die section what temperature profile you want. And that again we decide based on TG, melting, and degradation temperature of the polymer. Once you have the filament, which you can see it here. So this is the extruded filaments before sending it to a 3D printer. So this is of HDPE. This is HDPE with fly ash cyanosphere. This is an elastomer filament which we also extruded. Then we feed it these filaments to a printer, wherein printing temperature, chamber temperature, base plate over to which you deposit the material, and the printing speed need to be tuned. So as part of the syntactic foam development pertaining to this filament, I'm going to talk now. We did extrusion, and this is the first sample of the filament, which is not a good sample. The reason is there is gradation of cyanospheres from core to the end. The diameter is also variable one. This is a micro CT scan which clearly tells you the cross section. So that means that we need to modify or optimize or find out a suitable extrusion parameters. We did so, and finally we got these good filaments which are 2.85 within plus minus 50 microns. Now this is the filament, and you can see small micro balloons here. If you follow the cursor, a pointer, you can see here one, here second, third, fourth. There are many. In addition, you can see these void pockets. These are air pockets, and these are because of the machine limitation. As I mentioned, the machine what we have, single screw extruder, is a non-vented type, and thereby the flue gases gets entrapped. Interesting to see is that these flue gases which are entrapped or air entrapment is been uniformly distributed. So we have reported that as well. And such voids are beneficial for damping applications, shock absorber application, compressive applications, but definitely detrimental from the strength perspective. So if you want to, you can induce these, you can eliminate these based on the application. This is 40 by weight in HDP matrix is this filament, 1 time extruded. 1x means 2x is this, meaning the 1 time extruded filament, this one, we chopped it again, palletized it again, and again extruded, and that becomes 2x here. And this one more cycle, 3x. Now 1x, 2x, and 3x, we did that to check the recyclability potential of the developed filament, number one, and to check how many micro balloons have been survived, so that we can have that syntactic foam or lightweight effect. So this is an additional exercise what we did at that time. No doubt there are few failures, and those are also quantified. and reported in our all previous publications. We can do the CT scanning as well at 3 different planes of any material system and look around how the distribution goes. Because these fly ash cyanospheres are naturally burnt one, they have a lot of surface defects on the surface within the wall also. This is the broken cyanosphere. If you can see this, the wall thickness is variable and even the wall is porous. So when you do the micro CT of this, though the microballoon is intact, it seems to be broken because of these inbuilt wall thickness porosities. So we need to interpret the micro CTs also carefully. Now, once you develop this filament, before jumping into 3D printing, you need to have a counter check. And that counter check we did here. I'm sorry. We did here. So we compared the filament. I repeat, the filament, which is 2-time extruded, 3-time extruded with the injection molded sample. Now, what do you mean by injection molded sample? It is 165 in length, dog bone type, strip type. So we have compared the filament which is developed with the full-fledged dense sample. And this is one counter check probably is advisable before jumping into 3D printing after filament extrusion or filament development. And what did we see is 3-time extruded is performing better than the 1-time virgin injection molded sample. So this means it definitely makes a sense to utilize this filament for 3D printing, wherein definitely the 3D printed part is going to perform superior than the injection molded sample. So this probably is a good counter check that all of us can do whenever we have the developmental efforts. And here the same filament is been tested for 3 different strain rates. ASTM standard says 1 strain rate, but you can always increase the strain rate or decrease it, which will give you additional insight of material behavior. So how does these values signify to physical applications? I'll just take one simple example. 10⁻⁻⁴ is the slowest rate of loading. Relatively 10⁻⁻² is higher strain of loading. Let us take a simple example of a shoe sole or slipper sole. The sole, when you're standing, is having the compressive load at 1 fixed strain rate. Now, with the same shoe, when you start walking, the strain rate changes, goes little high. Now, with the same shoe, once you start running, the strain rate again goes up. And that's how it is going to be useful if you do your any mechanical test at different strain rates, which gives you an additional insight that if the strain rate changes, how the material behaves. And this is what we do for the sole developments, wherein material development, wherein we need to look around the different applications at different rate of loadings. So this is an additional thing which all of us can do once we develop a new material system. So this is once you develop a 3D printing filament, once you get assured yourself based on a tensile testing of filament as compared to injection molded sample for the same material composition, that the filaments are doing well, then definitely you should venture into 3D printing, because that gives you an assurance that yes, the time and the development efforts spent are worth to look around the 3D printing. Now, as we are handling altogether a different material system than commercially available material systems in the filament form, the issues with other parametric optimization or choosing suitable parameters comes in. Now, what you have in 3D printing regime presently, if you look at polymer base, you have HIPS, ABS, PLA, all these filaments are readily available. But if you want to try out some different material system, these things are bound to happen. And this is what has happened. When we start printing HDP, these were multiple defects here. Warpage was too high. This is the base plate, which also warped in addition to the sample. So after half of printing of the sample of around 1.5 millimeters, the sample warped and while warping, it made the base plate also to warp. So all of us know, whichever material you are printing, the compatible material paste you need to prepare and put it on the glass bed of the 3D printer. So we had a HDP plate because we are printing HDP. And this is what we observe. So you need to tweak in the parameters, as I mentioned, printing temperature, printing speed, chamber temperature, and bed temperature. So we tweaked in, and then we could able to get such a good, nice sample, which is made up of high density polyethylene. Then we compared the same high density polyethylene prepared using injection molding, compression molding, and 3D printing. It is the same grade of high density polyethylene. Now, if you see the tensile, when we apply a tensile load, the behavior is ductile in injection molding, brittle, and the combination of these. And by looking at these failure features, you can immediately even figure out that 3D printed HDP will definitely might have done better as far as the tensile moduli is concerned. No doubt straining is low, but load carrying capacity might be really, really good, or even the modular system will be really good. So what you see here is the HDP and its scanning electron microscopic image. We do this for as received systems to look around the texture. And this is the bunch of glass microballoons which look around like this. These are engineered ones having a diameter of around 15.3 microns, which we are going to now mix. What I talked previously was Sinosphere. I'm now talking about the glass. So this glass we're going to mix in the high density polyethylene. So high density polyethylene, we prepare a blend of glass in HDP matrix. So what we are going to look around now henceforth is manufacturing of a sandwich in one go using a 3D printing. Now for manufacturing of a sandwich using additive manufacturing or 3D printing, we need to use two materials, one for core, C-O-R-E, and another for skin. So here we are keeping the skin as a high density polyethylene and core as the mixture of these two. So the blends of HDP and JMB are prepared using a Brabender. I have shown it to you in an earlier slide to develop the feedstock foam filament. This is that feedstock foam filament for 3D printing of sandwiches. Now blending is carried out at an optimized speed based on our earlier works. What we decided is to have a speed of 10 revolutions per minute at 160 degrees C. And we varied around glass microballoons in the range of 20, 40, 60 by volume in HDP. And we designated them as H20, H40, H60. 40, 20, 40, 60 are the numbers of glass microballoons or reinforcement or filler by volume in HDP. And H word is from HDP. So that's how we designated or denoted it as H, capital H for Hyderabad, H20, 40, 60. So these, once we blend this, the pellets of these foams are dried at 80 degrees C in an oven for 24 hours before gravity feeding into the hopper of a single screw extruder. I've shown that to you as well. The quality of extruded filament depends on the extrusion system parameters. What I mean by that is a barrel temperature, die temperature, screw speed, and takeoff speed. We chose the suitable barrel and die temperature to convert solid pellets into semi-solid state and extrude it from the die without any material blockage and a breakage. As I mentioned earlier, the filament size depends on the extrusion rate, that is the screw speed, takeoff speed. HDP and foam pellets are fed to the screw and we draw the filament of 2.85 plus minus 50 microns to be fed to a 3D printer. Now, all these parameters are chosen by considering HDP melting temperature, uniform and homogeneous mixing of GMB in HDP without breakage, and the rheological behavior of blends, and also the presence of porosity, if any, during extrusion. And what did we find is in our studies, with an increase in GMB content, white percent do increases, as I said, because the extruder what we used was non-vented type. And it is in the range of around 5 to 6% for extruded all the filaments S to S60. Now what happens is, as I mentioned in one of the micrographs, these additional porosities or air entrapments, if this gets transferred to printed samples, they form a three-phase syntactic foam, which might enhance damping capabilities. And this is what figure 2A represents, a circular cross-section of extruded H60 filament. Figure 2 number 2 is here. Uniform dispersion is seen. This is cut by a knife, and thereby the knife edge or mark comes in here. And as the knife moves ahead to cut the filament, the flow lines follow the same direction, and that is also been seen here. And 2C is the extruded filament, which is having glass microballoons by 60 volume percent in HDP. This means 60 volume percent of HDP virgin polymer itself is saved. Then we went ahead with the sandwich manufacturing. As all of us know, sandwich composites are manufactured in two-step process. First, the core is manufactured, and then the skins are wet by an appropriate resin placed below. Then solidified core is placed on the top, and then the top skin is again placed onto it. Mold is closed 24 hours or based on the curing temperature, and then we get a solidified sandwich. Now what happens is, in this conventional manufacturing process, at the skin core interface, the adhesive, which is in the form of epoxy resin, is present, and thereby many of the sandwiches fail at the skin core interface. So if you have a methodology of producing the skin, core, and skin in one go and in one step, probably you are completely avoiding that common delamination failure between the core and at the interface of the skin and core, and completely looking at enhancing the sandwich performance. And this we exploited in 3D printing. So what I'm going to talk about next few slides is how did we do 3D printing of sandwiches. So here in sandwiches, we have a bottom skin. It is depending on the skin thickness and total skin thickness, what you want, number of layers will be decided. And then we have a core, and then again back to skin. So as I said, the sandwich structure consists of a skin, upper skin, and a lower skin, and a core is the middle portion. The printing parametric optimization is again carried out for the core first, being thicker. The filament having the composition of H to H60 are fed to fused filament fabrication based 3D printer. I have shown that 3D printer in one of the earlier slides. So what we did, we have H20, H40, and H60 bundles of filaments, which will be acting as a core. And then we have, here. We have pure HDP filament, which acts as a skin for the sandwiches. So we feed this in one nozzle, HDP filament, and we feed the foam filaments in the second nozzle. So we exploited the second nozzle, which is supposed to be used for support material, we used it for the core to print multi-material system. So what we did is, as 3D printer has two nozzles, we can say primary N1, N for north, and secondary N2. N1 and N2 are fed with, as I mentioned now, HDP and foam filaments. Both nozzles are utilized while printing the sandwich. And while printing the sandwich, N1 deposits lower skin. This is N1. Central portion is N2. And again, N1 comes in picture. And this is how we prepared a sandwich. And we can code them as SH, S for South, H for Hyderabad, SH20 if the core is having H20, SH60 if the core is having H60 as the filament which has been fed. And then you can decide the suitable dimensions for whatever test you wish to do. And then based on that, build a model, send it to appropriate software, which will create a still file. The G code can be sent to a printer to print all this. And before that, we did do the exercise of finite element simulation using ANSYS. So the 3D printing, as we all of us know, 3D printing involves complex heat and mass transfer phenomena that affects the dimensional accuracy of the final part. So we carried out the thermomechanical FE simulation using ANSYS. We fed the properties of skin and core independently. We defined the elements at the interface, merged the nodes at the interface, and followed the regular procedure laid down for analyzing multi-material system in ANSYS. And then we found out the temperature profile that I'll show it to you later. So with HDP filament and H20, 40, 60 foam filaments, based on the different parameters, we need to freeze a suitable printing or processing factor for realizing HDP with 20% glass microballoon, 40, 60% microballoon, or even the sandwiches. And this table shows the range of values we use for finding the suitable parameter. And what is that suitable parameter we found in a square bracket? Whatever material properties we used in FE simulation are also presented here. So whenever we try to go for a new material system, we need to choose a suitable substrate. That is, what solution you are going to prepare on the glass bed, or what is that material you are going to use on the glass bed onto which the first layer will be printed. And that is what it shows here. So we tried many options like HDP tape with bed heating, without bed heating, with bed heating, Kapton tape, and then ACBS block polymer, monopolymer on the bed with heating and without heating. So what gave us the best one is ACBS with bed heating. And this is also reported in one of the earlier literatures. So the substrate is finalized. That is created on ACBS FG1901 plate as to be laid down on a glass plate over to which we are going to take the first layer of HDP. Then we went ahead with adhesion. For what are different parameters, errors comes in picture. Now I'll refer pertaining to figure numbers here and the respective figures. So we are talking about figure 4 now. So the adhesive bonding between the first layer of the print and the substrate depends on especially in 3D printing of polymers, bed and a chamber temperature. You can look around here. We have a bed temperature and we have a chamber temperature. The ranges which are found out to be suitable. So what figure 4a represents is a representative print image after peeling the samples. Peeling meaning removing the samples from the substrate at different bed and chamber temperature. What we saw is the improper adhesion is resulted in non-uniform surface texture in case of 80 degrees C bed temperature, and for chamber temperature ranges of 45 to 75 degrees C, as you can see it in figure 4a. This is the best. Increasing bed temperature to 100 degrees C, improper raster diffusion at the base layer forms rough surface and void formation. You can see it here. The perfect bonding, uniform texture, good quality sample without any defect was observed at 120 degrees C. The uniform and the same texture on the bottom and uppermost layers of the printed samples are very crucial to render similar stress state under applied loads. So the chamber temperature plays a vital role as well in controlling the delamination at the skin core interface, the marked one here, or within the layers, the marked one here. So this is what the defect-free sample came out based on the permutation and combinations. And this is how it looks like in scanning electron microscopy. When you take an SEM onto the edges, the bad ones, and you can see clearly the skin and the core are separated at this interface. There are some intra-layer gaps as well. But once you tune these parameters, you get perfect bonding between these layers. And we can look around through SEM as well. Then we looked at once we get the defect-free sample here, related parameters are freezed, and then we touch the next parameter in sequence. So now here again, you see the prints through N1 and N2. N2 is for our foam, N1 is for our neat polymer. So HDP filament is been fed in N1, foam filaments are fed in N2. Again, if you go on changing the temperature, this is what different defects start creeping in. At one temperature, a good sample comes out, a sound sample comes out. The similar way you can see a multiple lands here, voids here, sorry, pockets here, lands here, and at 245, the course resulted well through N2. So again, now these two parameters are freezed, and then we start with the next one, which is commonly called as a prime pillar. Now this, especially when we're talking about printing of sandwich structures, using a single nozzle system, it is a difficult task in the sense, I'm not saying it is not possible. Using the same nozzle, you can print a sandwich as well, but you need to keep on changing the filament. And there is every chance that in case of multi-nozzle system, the second nozzle might not start precisely at the same location from where you need to start. So thereby we print additionally, and then we cut it off, and that is known as a prime pillar. This is without prime pillar, wherein the deposition gets improperly laid. But with the prime pillar, as defects is localized to an additional part which can be cut later, we can get a good sample. So this is one more facet what we can look into. Most crucial is a warpage. Warpage during printing, which I have shown it to you earlier. So warpage during printing is this. I'm talking about this. This you need to address an issue when you are into material development or 3D printers, which is our present focus at the lab, or the warpage post printing. So once you address the warpage during printing, next comes warpage post printing. Now this is the sandwich sample which got printed. Okay, this is what you see. While printing, it perfectly prints. And after printing, as we leave the sample onto the bed to cool, the complete sandwich bends like this. You can see there is no interface failure. We did not observe in a sim, neither by naked eye, between the skin and core and the skin subsequently. But what did we observe is such warpage happening completely post printing. So for that, we need to look at the suitable chamber temperature. Many printers are open architectures wherein it is not possible, but wherein you have an enclosed chamber, therein you can play around the chamber temperature so that you can maintain a proper gradient during cooling or annealing process, what we call it as, and then choose a suitable parameter which will give you perfect sandwich sample. You can see the color differentiation here. This is skin, this is core, and again there is a skin down line. So this is how we can perfectly produce the sandwich sample. In addition, though the layer offsetting is an machine dependent parameter, we need to keep an eye on this. This is nothing but the distance between the two nozzles. If the machine is being used very often, we need to look around this offset. If you don't look at that, there will be an offset like this. And this offsetting is a machine dependency parameter, which you need to look at and set it, compensate that. And if you compensate, your samples will come good. Then depending on the printing speed, yes, this is how the samples show defects at different printing speeds. At a suitable printing speed, you will get a perfect sample without pockets, without lands, without scrubbing off your nozzle into the system which is being made. So we need to look around all these parameters when we are really looking around different material system. This is how the scanning electron microscopy of this sandwich is. So the micrograph is taken in the skin portion, then between skin and the core at the interface, then at the center of the core, again core and skin interface, and in the skin. This is how it looks like. You can see this is a skin, this is a core, and skin. These are for non-suitable parameters. How does it look like? For suitable printing parameters, all these residual microporosities goes off, and you can see a seamless interface between the skin and the core, and the skin. And on the edge, you can clearly see in micrograph something like this. So this is how it looks around, and you need to have all these printing parameters to look around to finalize a good quality sound sample. Then, as I mentioned earlier, we did the finite element simulation, and the sole purpose of doing this simulation was to understand the residual stresses in the system, especially at the skin and core interface. It's a simple one. We found out different stresses, distribution along the thickness, across the thickness, and most importantly, we wanted to know this: the temperature and the stress distribution in the sandwich which is being printed. So whatever printing parameters we mentioned as a suitable, the same printing parameters, same boundary conditions in the form of a temperature we applied, simulated a finite element model, and this is what we get the temperature distribution, and this is what we get the stress distribution. Experimentally, getting the stress distribution in the sample is difficult, and that's why we chose this finite element simulation route, wherein you can see at the skin and the core, there is a drastic change in the stress. Same here. In the core, it is almost similar, but no doubt, from the bottom to center and from center to the top skin, there's a slight change in the slope. The basic intention behind looking at this is, can we do something so that we can reduce this drastic change here, this drop and this rise at the interface? And are there any possible avenues? There are many possible avenues, like you can put a blower during the bottommost skin and the first layer of the core is getting printed, and many others as well, wherein you can try to find it out and you can try to minimize this stress distribution. And that's how this such finite element simulations or thermomechanical analysis simulations helps us. So with this, I'll stop the presentation. And this is what I presented as part of my research group, what we did and what we are doing as part of different systems in 3D printing. So I thank again for all of you for listening patiently. If there are any questions, please let me know.
With me, I can convey to sir.
In chat box, if anybody has.
Yes, sir.
Yeah, I'm looking at that. Yeah. Or even if you have an access to a chat box, you can write a question there. Else, you can find in my email ID on NITK website and push you whatever questions if they come at a later stage. I'll definitely will respond to them. Yeah, I think one person has raised. Please go ahead. I think Sir Satyabodh Raichur has raised a hand.
Yes.
Or probably accidentally he might have raised the hand as well.
He's an
Okay, yeah. There's a question in the chat box. What
Yes.
are the parameters required for filler material to bind with PLA? Required for filler material to bind with PLA. Okay. So, need not have to be only PLA. You take any polymer, any reinforcement. Try to find out the chemical composition. And then based on that, you can decide the suitable chemical to be treated either on the filler or on the polymer, and then you can go ahead, then definitely you will have a good bonding. So as far as the sinospheres are concerned, we are using a silent treatment. If I only merely, just for an example from my experiences, so if I just use a silent treatment on sinospheres, bonding is good. But if you still want to go for a higher level of bonding, you need to functionalize the polymer as well. So likewise for PLA also, whatever filler you want to utilize, try to find out the composition, and the common group has to be present in the chemical which will bind both of them. I hope I have answered your question. So we need to little go and peep into the chemistry part. Just find out the composition. It will give you idea what are the open-ended bonds, and then try to close them. And it is true for any polymer, any filler. Yes. think there are no more questions, I guess. Saying any? Okay, fine. I think there is no more questions, ma'am. Yeah.
Yes,
Yes,
sir.
please.
Hello, sir. How are you going to validate your results, sir? You said you have done FEM
Yeah.
analysis.
Yeah.
But there is no experimental results to be compared with the FEM results. Stress, you said difficult to find out the stress and strain
Yeah.
experimentally.
Yeah.
You have given boundary conditions for FEM.
Yes.
But how you are going to compare experimental results? So validate your.
Yeah. So whatever finite element simulation we did, it is in the thermomechanical regime. Now, what I said is we can't experimentally measure the residual stresses experimentally. I'm not saying it is not possible, but it is very difficult. I think we know that many people use different approaches, drill the hole and put the probe and check it. So this validation and the comment is pertaining to the residual stresses. But or otherwise, you can do a simple 3-point bending test experimentally, and you can go ahead with the same boundary conditions, having these residual stresses, whatever plot I have shown it to you, and apply the same experimental loads in a 3-point regime in ANSYS, and you can compare them. The validation of residual thermal stresses is difficult. That is what I wanted to say. But otherwise, you can always, you can do a 3-point bend test. So with the same model, same boundary condition, you apply, rather now you have the plot of residual thermal stresses inside the system. So you give that as an input as part of the material property, and then you apply your regular 3-point bending load, and then you can compare the experimental with the finite element simulation. Definitely, it is possible.
Okay, sir. Thank you.
Thank you.
Hello, sir. Am I audible to you, sir?
Yes. Yes,
sir, this is Satyavod Raichu from APS College of Engineering, Bangalore.
Okay, go ahead, Professor.
Yeah, sir. Actually, I have a small doubt regarding the 3D printing technology for the PLA. So PLA are normally used for biodegradable properties. There are organic polymers which are widely used for the recycling process or maybe to attain biodegradability. So when we add some filler materials, maybe it may be aluminum or silica to increase the thermal resistance as a filler material. So how it can affect the biodegradability of the PLA, sir? Is there any measurement or a scale or any kind of experimentation to measure that biodegradability?
Yes, we do have. And we do that in vitro and in vivo studies whenever we develop implants. Yes. There are polymer scaffolds also. I can guide you to one company which does a lot of polymer scaffolding known as Osteopore.
Okay, sir.
These people are pioneers, having a pioneering metal compositions for polymer-based scaffolds. No doubt metal also they are doing.
Okay, sir.
Rather we call it as a bioresorbable magnesium implants. So we have polymers as well. So you can look at the Osteopore, and there is a way, there are tests, there are controlled conditions into which you can definitely find out the biodegradability. And it is very simple.
Okay, sir. Thank you, sir.
Yeah, welcome. But PLA is a little tricky material to print. So when you are printing, just choose your printing parameters judiciously. Especially we find a lot of blockage once you go at 280 degrees C or so.
Sir, is that nozzle temperature makes a lot of effect on this printing, maybe the PLAs and all? Is there any like the influence of the nozzle temperature, or maybe during the FDM process, the nozzle temperature is the most influential matter on printing of the material, sir, especially in PLA?
See, for any material, including PLA, Definitely nozzle temperature is crucial. Most importantly, the crucial parameter is how the nozzle is designed. What I
Okay,
mean
sir.
by this is there are nozzles with cooling systems. Okay. These nozzles are going to do the PLA job wonderful than the regularly available nozzles in little inexpensive printers.
Mhm.
Okay. So if you have a brass nozzle, probably that's what how the nozzle cooling is been taken care is crucial. I'll tell you why. See, ultimately, once any filament or any polymer, or for that matter, even the metal systems, once they melt, then that's all. The story ends there. They just go on following the code and they will deposit. But before melting, we need to guide. If you talk about the polymers, we need to guide the filament into the nozzle head wherein the heating is taking place. Now, what happens is, though you have PTFE tubes, what you see the tubes which are in the white in colors, this PTFE tube is being inserted into the nozzle. Now,
Okay.
for some applications in PLA, let us say you are mixing any other filler like a metal, because we did that. We mixed the stainless steel, brass, copper, everything. So when you mix the metal powders in polymers, the temperature profile changes than the virgin polymer. You need to raise the temperature of the nozzle. Now you will raise it to 280 degrees C. Now at 280 degrees C, what happens is the filament, the PLA filament which you are feeding into the nozzle is being surrounded by a PTFE tube. Now this PTFE tube itself starts burning and starts melting. Now when the PTFE tube starts melting and burning, it poses the restriction for PLA filament to be fed inside the nozzle through your motor. And there the nozzle blockage comes in. So thereby, if you have a nozzle with cooling system, the PTFE burning and disintegration is stopped, and even you can go to 350 degrees C. That's not a problem. So if you are coming across frequent blockages, especially for PLA, then probably you need to relook into the nozzle. Nozzle temperature, no issue. You can, as I said, you can go, I have printed PLA at 300 degrees C, 320 degrees C. 280 I have started with minimum, because that was one specific one application. So here what happens, you need to relook into the nozzle cooling. If the nozzle cooling wherein the PTFE tube is coming is opt, then your PTFE tube is intact, PLA is fed continuously, and you can print PLA without any hassles. I hope I answered.
Yeah, sir. I got your point, sir.
Okay. Madam, I think there are no more questions, I guess. So anyways, all the participants can reach to me through my email ID, which is on the NITK website.
Yeah, this session is also.
Madam, we lost your voice in between. Madam, shall we close?
Hello.
Yes, you are audible, madam.
And synthetic foams.
Madam, we lost you. Madam, we lost you. Your voice was not audible in between. I don't know whether I have a problem here. Madam, are we closing?
Okay, sir.
Yeah. Okay. Thank you. Thank you, one and all. Thank you to the AMC administration and madam for arranging this. Thank you. Good day.